All right, this is going to be the week 7 discussion focusing on conditional execution. Conditional execution is another name for making decisions. What we're going to learn about is that the computer is going to evaluate what we call a conditional or boolean statement, and based on the results of that statement, execute one block of code or execute a different block of code. Essentially, I liken conditional execution to teaching the computer how to make decisions. So let's think about what we've talked about so far in this class. We've created some very basic programs. We've added input and output to those programs. We have learned how to format our output. We've even learned how to store data, some basic data storage, at least for short term. And just in these last couple of weeks, we've looked at breaking down larger problems with the help of procedural and functional methods. So we've talked about methods, we've talked about storing data and creating variables, we've talked about formatting output, we've talked about input and basic output. We've even created our, your very basic hello world style applications. So today we're going to move on to something that makes our programs even more useful than anything we've created thus far. We're going to talk about what decisions or conditional executions are. We're going to define those terms for you. We're going to look at how we as humans make decisions and how we can translate some of those decisions so that computers can make them. Because obviously there are a lot of things that we do that we consider one step that are actually far more complicated in real life. We're going to have a discussion of relational operators because they help us get to these things called boolean statements. We're going to learn to use flowcharts to plot the path of a program. I think flowcharts are probably one of the best ways to visually illustrate decision making the way the computer sees it. And I think that it will be a big help in charting out the flow of your program when you get stuck and you don't know where your program is going to go or what it should do. Then we're going to look at making decisions in Alice. Specifically, we're going to look at the Alice if structure. It's very similar to the if structure in Java. We're going to look at Alice decisions with functions. So we're going to look at making decisions with functions that return true and false values. And then we're going to look at making decisions in Alice with variables or functions that return other types of data. So we have functions that tell us how far away we are from something. That's not a true or false value. So we have to use relational operators to turn that into a true and false value, and we'll see how we can do that. Continuing our objectives, or the things that we're going to talk about, we're then going to move on to decisions in Java. We're going to look at functional methods again, and there's a reason why. Functional methods return data, but functional methods can also give us true or false values, and those can be extremely helpful when we're trying to set up some sort of conditional structure or decision structure. Additionally, there is a method from the math class that we're actually going to use this week in some of our examples, and so I want to take a quick review of that particular function before we get started. We're also going to learn about decision structures in Java. There are two types of decision structures. Your very basic one, which is called an if structure or an if-else statement, and then we also have something called the switch. The switch has been upgraded in previous years. With Java 7, the switch now supports some new data types that we're going to find out about. However, when you read in your book may tell you that some of the stuff I tell you isn't possible, and that's going to be because it was added in Java 7 and not everything has been updated for Java 7. But since we're using it in class, I wanted to introduce you to some of those concepts. We're going to learn about making our decisions, the actual tests that we're making, a little more complicated by adding this idea of logical operators. But before we get into all that, because most of that probably sounds like Greek to you at this point, I want to just get us to think about decisions. And I'm going to do that by giving us some examples of human decisions and things that the computer would need to do in order to make those decisions. But first, before we even get into that, let's define conditional execution. Some condition, like the value of a variable or the result of a function or a functional method, is checked for being either true or false. If that condition is true, one block of code will be executed. If that condition is false, another block of code will be executed. Sorry about that. This, in a nutshell, is conditional execution. The idea that we are going to evaluate some data, and based on our evaluation of that data, the computer is going to decide whether to go one way or another. Now, there isn't really a third way. When you do a test, these tests are set up to either be true or false. Now, we can set up some more complicated statements, but essentially these are either true or false statements, period. There is no in between, sadly. Let's think about these decisions as a human. I'm going to throw up some questions or decisions on the next couple of slides. And I want you to think about what you would do, how you would evaluate whether or not these things would be, how you would answer these decisions, how you would decide what to do. So let's look at decision number 1, going to the movies. You're trying to decide whether or not you want to go to the you can go to the movies. To help you with your decision, you pull out your wallet. If you have enough money, you will go to the movies. All right. So how do we determine if you have enough money? How do we determine what you would do to go to the movies? Well, I would look in my wallet. If I have a 20, I could probably go. If I only have 5, yeah, I'm probably not going to be able to go, especially since I closed the Maxi Saver. But what all goes into that? Let's think about another decision. Stopping at a light. You drive down Route 885 and you're approaching a stoplight. As you approach the light, you start thinking about what you're going to do. If the light is green, you're going to continue through the intersection. If the light is yellow, you're going to start to slow down to a stop. Although here in Pittsburgh, some people might gun it, but we don't want to do that. If the light is red, you want to stop so that opposing traffic can proceed. Think about how you as a human being make that decision. What are the things that you do when you're making this decision? You look at the light. You remember back to the information that you learned in the driver's ed manual. And then you make a decision. Then you find the brake pedal. Then you push on it. There's a lot of steps involved for something that seems relatively trivial for us. Third one, some traffic decisions. You're driving through the south side of Pittsburgh. All right? You're going through Southside Flats. And you're trying to decide what you're going to do to try to get around traffic. If you get stuck at 23rd Street, then you're going to turn left. If you get stuck at 26th Street, however, you're going to turn right. Think about all the thoughts. Think about the entire process that goes into making that decision. All of the things that must be checked. Are you stuck in traffic? Is this rush hour? Where are you along Carson Street? All of these things go into making that decision. Something that seems, again, relatively trivial to us is a little more complicated to explain to the computer. Let's look at these again and think about them from a computer perspective. Before we do this, though, I need to introduce you to a concept because it's something that's going to come up in some of these examples. Is this idea of relational operators. Sometimes, in order to get a Boolean condition, a true or false result, we have to compare data, whether that's constants, variables, primitives, or even objects. We need to make a comparison. Is something bigger than something? Is something the same as something? We need to be able to make these comparisons and use those as the basis for our decisions. Because we're not always going to have true and false questions, true and false methods available for us, or variables that contain true or false that can make these decisions for us. Sometimes we have to analyze data and look at the values of data. And so we have these things called relational operators. The first operator I want to talk to you about is equality. In Alice, we're going to see an equals, spelled out as E-Q-U-A-L-S. In Java, we'll see that as double equals. Now, I want to let you know of something in here. When you see these operators and you see double operators, you have to type them into Java exactly as you see them on here. There is no space between these operators. Otherwise, it would mean something completely different, and the compiler may not understand what you're talking about. So when you see double equals, it's equal sign, equal sign. That's it. There's no space in between them. You can have space before, space after, but no space in between. So that tests for two items being equal. Equal means they're the same. If they're variables, they contain the exact same value. Not equals, on the other hand, is a little bit different. In Alice, it's an equal sign with a slash through it. In Java, it's an exclamation point, which we'll learn is not later, and the equal sign. Again, no space between the exclamation point and the equal sign. And it means the two items are not equal, or they're not the same. They don't contain the same values. Something that you may have seen from your math days when comparing numbers is less than and greater than. And we have less in programming, we have less than and greater than, and we also have less than or equal to and greater than or equal to. And I'm going to look at those quickly now. So if we look at the less than operators, the item on the left side of the less than sign is going to be smaller than the item on the right side. In order for that statement to be true, in order for that statement to be true, then the item on the left side must be smaller than the item on the right. In order for the statement that is being presented to us to be true, with not equals, that means the item on the left has to be different than the item on the right. And when we're talking about equals, the item on the left and the right must be the same. When we're talking about less than, again, the item on the left has to be the smaller value, or that statement isn't true. Less than or equal to gives us a little more leeway. The item on the left has to be smaller than or the same as the item on the right. Greater than, exact opposite. The item on the left has to be bigger than the item on the right. And greater than or equal to, the item on the left has to be bigger than or equal to the item on the right. And those are the basic relational operators. And we'll use these operators between values to give us a boolean statement. That means that statement's either going to be true or false. We may know it when we write it, or we may not know it until the code executes, especially if we're dealing with variables or user input. We may not know the outcome of that until we get the user input and see. So let's look at, now that we have these relational operators, let's look at the computer's perspective of making a decision go to the movies. So here's the situation again. You're trying to decide whether or not to go to the movies, and to help with your decision, you pull out your wallet. If you have enough money, you'll go to the movies. So what all do we have to do to teach the computer to do this? Well, first of all, the computer needs to find out how much money is in your wallet. If the computer has a virtual wallet, it would need to check that. So we would need to provide it instructions to go out and check that virtual wallet to find out how much money it has. Then we need to find out how much the cost of a movie ticket, and I put in a drink, but even a snack. I can usually get through the movie without eating anything, but I usually do want something to drink while I'm sitting there. So I'm going to need to know, in order to make this decision, what is the cost of a ticket and a drink? And quite frankly, that could be upwards of $15 if you've been to a movie theater lately. Then I have to make a comparison. Is the amount in my wallet greater than the cost of the ticket or the drink? And we could probably say greater than or equal to would be okay, although I usually like to have some change to spare. But that's the process that the computer's going to have to go through in order to make this decision. And in reality, this is the step-by-step process that you and I would go through to make that same decision. If the amount in my wallet is greater than the cost of the ticket, then I can go to the movies. However, if it is not, then I got to stay home and watch TV. Let's look at the stoplight decision, right? All right, you're driving down to 885, you approach a stoplight. You start thinking about what you're going to do. If it's green, you can go. If it's yellow, you got to slow down. And if it's red, you got to stop. So how's the computer have to think about this? Well, the computer's got to get the status of the light. What is the current color of that light? If the status is green, then you can keep on going. But if the status is yellow, then you got to slow down. And if that status is red, you got to stop the car. So here again, you can see that I'm actually using this idea of relational operators to build these statements that I can test against. I can look at that light and find out what the status of that light is. And then I can say, is that light equal to the color green? And if it is, I can keep on going. Now keep in mind, this is more in the lines of pseudocode, right? We're not talking actual Java statements. I'm just getting you into the idea at this point. I want you to start thinking about how the computer makes decisions so that you can better plan when you go to write your programs. Keep in mind, if we're looking at this, right, that light is either green or it's not in this first statement. If we look at this first statement right here, that light is either green or it's not. If it's not, then we can proceed down to the next test. But it's either true or false. There's no in between. If it's false, we can test it for something else. We can test it to see if it's yellow. But even here, this is going to be either true or false. The light is either, if it's not green, then we go down and test, is it yellow? And it's either going to be yellow or it's not going to be yellow. Well, if it's not yellow, then we can come down here and test it for something else. So no matter what, the computer really only understands when it comes to decisions, true or false. If it's true, we can take one action. If it's false, we could test for something else or do something else entirely, like we did in the previous example. In the previous example, either I had enough money or I didn't. And if I had enough money, I was going to go to the movies. And if I didn't have enough money, I was just going to stay home. Now, I could have found out maybe I have enough money to go out to the mall and buy dinner at the food court. When I was in college, that used to be the highlight of my week. Going on Saturday to the food court and having dinner that wasn't dining hall food. That used to be the highlight of my week. So, just something to think about. The computer really only understands true or false. I've even got a little more complicated one for you now. Traffic decisions. Let's look at this one again. You're driving through the south side of Pittsburgh. You get stuck in traffic at If you get stuck in traffic at 23rd Street, then you're going to go left. If you get stuck in traffic on 26th Street, then you're going to go right. And so this is an even more complicated decision. First of all, I need to know, am I stuck in traffic? Then I need to find out where I am. And if I'm stuck in traffic and I'm at 23rd Street, I'm going to turn left. But if I'm stuck in traffic and I'm stuck at 26th Street, I'm going to turn right. We're going to talk about logical operators shortly. They let us build these bigger and more involved decisions. But basically the idea is both of these, both this part and this part, have to be true in order for this statement to be true. I mean, it makes sense, right? I only want to turn if I'm stuck in traffic and I'm at 23rd Street. And in this case, I only want to turn if I'm stuck in traffic and I'm at 26th Street. Both of these have to be true. The reason they have to be true is because of the and. But basically, I can set more complex decisions up. I can ask the question, am I stuck and am I at 23rd? And if both of those are true, then I'm going to turn left. And if I'm stuck and I'm at 26, then I'm going to turn right. We'll learn about logical operators here towards the end of the presentation. But just to give you an idea. One of the ways that we can sort of map these decisions out before we even start writing code is through something called a flowchart. A flowchart is a diagram that shows the steps of a process or algorithm. Each step is depicted as a rectangular box. Every decision or conditional statement is denoted as a diamond. And the starts and endings of a particular algorithm or program are usually denoted as ovals. When we're getting input and output, it's usually denoted by a parallelogram. And sometimes, if you're looking on a really complex, you'll see a rectangle that has two lines on the left and right side. That indicates that that step is actually documented in another flowchart for, say, a method. Maybe you have a number of methods in your program, and there's one flowchart that shows the main flow of the program, and then and it might call a bunch of methods, and each of those methods are documented in other flowcharts, or in the document, or maybe in other documents, and the double bars on the left and right side illustrate that. I'm not getting into that much detail at this point. I'm not here to teach you flowcharting. I'm here to give you tools to help you better build your programs. So let's take a look at the actual shapes. Again, the start and stop is sort of an oval. The parallelogram shows the input and output. Just a step in the process is shown as a rectangle. And the diamond shows us a decision or conditional statement. Let's take a look at the movies. I went ahead and did a flowchart for our sort of can I go to the movies program. And you'll see I have a start. I do not have an end. I should have put one in, but I did not. Anyway, we have a start. And the first thing I need to do is find out how much money I have in my wallet. The second thing I need to do is find out what the cost of a ticket and a drink are for me. It might be a ticket and a snack for you. Then I need to make a decision. Is the amount in my wallet greater than or equal to the cost of a ticket and a drink? And if that conditional is true, the amount in my wallet is greater than or equal to the ticket and the drink, then I can go to the movies. If it's false, I got to stay home. I can't go. So here's a basic flowchart, and I must say I really can follow this. The idea with the flowchart is that it has arrows, and those arrows indicate the flow of the program, not necessarily the flow of the data, but just the flow of the process. So you can see from the time the program starts, we flow to the next step is the figuring out the amount in my wallet, and then we have an arrow that shows us that the next step is the cost of the drink, or the ticket and the drink, and then the next step is making the decision, and then the decision will go one way or another out of the diamond based on whether or not my conditional is true or false. That is how we can think about making decisions, and thinking about making them when we're writing a program, I think, is probably the most important part. One of the things I have students consistently asking me is, why doesn't my program work? And one of the things that I spend a lot of time with them is, yeah, their code isn't right, but their code isn't right not because they messed up the syntax of their code, but it's because they didn't spend long enough time thinking about what they wanted the program to do. Once you figure out what you want the program to do is, finding the code becomes infinitely easier. And learning to think about how the computer makes decisions will help you when it comes to writing your code. Let's talk about making decisions in Alice. I think Alice is one of the easiest areas to make a decision in because Alice doesn't really let you screw it up. That adds some issues, but I think it's really pretty helpful. When we're making decisions in Alice, we have one sort of decision structure. It's an if statement. And you can see a picture of the Alice window here. If you look right here towards the bottom, you see the code window here. Your scene is here, and you've got the procedure and function box here. At the bottom here, where we would normally find our comments and our variables, which we've done so far, you'll see there's a little thing called an if. I've put a red box around it in this diagram, or in this picture. I went ahead and put a red box around it. That if is the decision structure in Alice. So if we look at an example of this, as you know, in Alice we have functions. They're on the function tab. They give us data back. Some of these functions give us back true and false values. Some of them just give us back a numeric or a string value, or even a joint value, which is a joint on the model that we can manipulate. In this case, what we're seeing is the use of the is facing method. The in facing method basically says if the cow is facing lioness and one object is facing another, and that statement's either going to be true or false, because either the front half of that object is looking at the front half of the other is looking at the other object, or is pointed to that other object, or it is not. There is no in between. It either is or it isn't. In this case, the statement says, if the cow is facing the lioness, then move the cow away from the lioness. Otherwise, move the lioness away from the cow. So if the cow is not facing the lioness, then the lioness goes off on her own way. If the cow is facing the lioness, he's going to back off because he doesn't want to get eaten. So you can see here we can use a functional method as our test, as long as that functional method returns either true or false. Now, if that functional method happens to return data, then we have to treat it like it was a variable or another number. We're going to have to use our relational operators. So we can turn the results of that function, into a Boolean statement. So if the lioness's height is less than 0.5 meters, then I'm going to move the cow away. Otherwise, I'm going to move the lioness away from the cow. What I'm saying here is get height is a method. It's a function. It's a functional method. It returns to us a decimal number that is the height of the object in meters. So I can't just say, if the lioness get height. That doesn't result in true or false, so it's not going to work. So in order to be able to use it in the if structure, is that test, then I am going to have to turn that into a statement that results in true or false. And this is where our relational operators come in. When you're working with functional methods, if those functional methods return true or false as their return type, then you've got no problem. You can use them. You can ask the question, did this method return true or did it return false? However, if that method, like getHeight, returns data, a numeric value or string value, anything like that, then we have to use our relational operators in order to make a decision. We cannot just put it in there. It's not going to work. A number is not true or false. It's just a number. Let's think about decisions in Java for a moment. Before we get started into that, I want to do a quick review of functions. Functions, again, are methods that return a value. We've looked at that already in Alice. When making decisions, we need a Boolean value. We need a value that results in true or false. A function can return a Boolean value, or we can use relational operators to create a Boolean statement. And again, we've seen that in Alice. One function that we're going to be using is the random number generator. We talked about this last week when we talked about functional methods. The random number generator is a really useful functional method that returns a number between 0 and 0.9999999 repeating. And that's all fine and well. And in some applications it may even work for us. We're going to be using it today in a demo program that that's not really very useful for us, so we're going to manipulate that a little bit to get numbers that we want. Now that we've had a little reminder about functional methods, I want to talk a little bit about the decision structures that we have in Java. And there are two types. There is the if-else structure, which is probably the most basic type of decision structure in Java. And then we have the switch structure, which is really, really good when you have when you want to test one thing for equality against a large number of items. Let's first take a look at the if statement. The if statement is probably the most basic decision statement in Java. Any decision that we want to make, we can make with an if statement. It allows us to set up a Boolean test. And if that test is true, take one action, and if that test is false, take another. It works very much like the if structures that you saw in Alice. And as a matter of fact, if you have the Alice plugin installed in NetBeans, there is a way, there is actually a pre-set up if structure that we can drag and drop into our Java programs. Let's take a look at an example of the if statement. This is sort of an anatomy and physiology look at the if statement. You have the keyword if. Then you have a set of parentheses. Inside that set of parentheses is the thing you want to test. It's your statement that results in true or false. That means it can be a method call to a method that returns true or false, or something that relies on a relational operator to get you a true or false value. Then you're going to have a set of curly brackets. This set of curly brackets, the first ones that you see, block out the statements that are going to be executed if that test is true. Then, then you will see the else statement, and you will see another set of curly brackets. Else is a keyword, and you'll see another set of curly brackets that come after the else, and that contains the code to be executed if the statement is, if that boolean statement, that conditional statement, is false. If it evaluates to false, then the curly brackets that come after the else are going to be executed. If it's true, then the curly brackets before the if statement are going to be executed. Or, I'm sorry, that come after the if statement are going to be executed. Let's look at an actual example. I have a variable x and a variable y. And I have said if x is less than y, if x less than y turns out to be true, if the current values of x and y turn out to make that statement true, then I want to print out the statement x is smaller than y. However, if that statement is untrue, I want to print out the statement x is bigger than y, because obviously if it's not less than, then it's got to be either equal to or larger. Now, I'm going to warn you, your book is probably going to show you the block of code that comes after the if and the block of code that comes after the else without curly brackets. It is legal in Java to write your decision statements without curly brackets if you only have one statement to execute for each block. So one statement for the true side, one statement for the false side. What I am going to tell you is you should always, 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 always use curly brackets. And I'll say it again, always use curly brackets. Because what you're going to do is you're going to find that you're going to wind yourself up in trouble. So always use curly brackets. I get that the book's not always going to do it. It is a shortcut. I don't like that shortcut. Everything that you see that I give you that is either created by me or created by Professor Wrigley is going to use these curly brackets because we think it's important that you do that. It really sort of delineates is probably the best word I can find where those statements belong. We can make our if statements bigger. If you recall back to the traffic light situation, where we had if the traffic light is green, if the traffic light is yellow, if the traffic light is red, we can expand this. We can make this a little bigger by saying if x is less than 0, then print out the statement is negative. However, if x is greater than 0, we're going to do something else. We're going to first check to see if x is equal to 0. And if x is equal to 0, then we're going to print out the statement x is equal to 0. Otherwise, if it's not less than 0 and it's not equal to 0, we're going to come down and execute the third else, which is sort of our catch-all, x is positive. Because of course, if it's not less than 0 and it's not 0, then it's got to be a positive value. But think about this for a moment. I just want you to think about all of this for a moment. If this statement is false, if the value of x is not less than 0, we're going to jump down here, we're going to come to the first else, and right after that else is an if. So we're going to do another test. And if this test is false, then we're going to drop down to the else and execute the statements that come underneath of it. That's the way that's going to work. We're going to fall through, but only if the test fails. And we can put as many additional tests in here if we want. We're only going to move down to the next test if the previous test is false. Otherwise, it's going to be true, and we're going to go ahead and execute whatever goes with it. I know that might be kind of complicated, but it's very important. The other structure that we have is the switch statement. It does the same basic job as the if. It is a little bit different. It's best when testing one item for equality. It has to be, we're looking for it to be equal to one of any number of items, especially when there's a lot of items. It really sets itself up for that. It is the better choice in that situation, but it is not. But it is not the only choice. You can use an if statement for that, but I think the if adds a lot of extra coding that we have to do, extra characters we have to type in order to get there. When testing the value that we're testing must evaluate to either a byte, a short, an int, a character, or a string. Your book and even your handout, the PDF reading that I give you, aren't going to mention string. String is a new addition to Java 7. The previous incarnation of the switch statement did not permit strings to be tested. Every other language allowed strings, but Java did not. Java has sort of caught up to .NET and C# and all of the .NET languages, and I think even C++ now allow strings. I know they didn't always. But now allow strings to be tested in switch statements. And basically, I got an example for it. It's going to run through each possible value and see, are they equal to? Are they equal? Is the test and the value equal? Is the test and the value equal? Is the test and the value equal? It's going to keep doing that until it finds a match. If it never finds a match, either we're just going to stop and continue on with the program, or you can also have an optional default statement, which I liken to a catch-all. If there is a default statement, then and nothing else matches, we'll go in and execute the default statement. It's sort of like an else. The other thing that you need to be aware of is once there's a match, it will execute all code that follows the match unless there is a break statement put in. So the break statement says, execute this code and stop. We're done once you've executed this code. However, sometimes we might want that, sometimes we might not. I'll show you a couple examples of the switch statement. Here is sort of a very general example. We use the keyword switch, and then in parentheses we have whatever the thing we want to test against, the value, the variable, the result of the function call, that we want to test against. And then we have a set of curly brackets, and inside that set of curly brackets we have what we call case statements. So we have the keyword case and then a possible value, a semicolon, the code to execute, and if we want it to stop executing once that code is done, we include a break statement, which is just the keyword break and a semicolon. And then we have the second value, the second possible value, the code for that, and then the break statement if we want it to stop there. And then maybe we have more of those, and they take the format of the keyword case, the value that we want the test to be equal to, a semicolon, the code to be executed, and then the use of the break statement. And we just keep doing that all the way through until we're done. If we wanted to do something in the event that none of those possible matches are made, we would have a default statement. It is not required. We don't have to have it, but I like it because it lets me. It's sort of a catch-all. It will if there is no match, we'll execute that default statement. It's not always necessary. You may not want it depending on the problem that you're solving, I have a lot of problems that I don't care. If it doesn't match if it doesn't match something in the list, then I don't want to deal with it, and that happens. So, but sometimes I want it to let me know that, hey, I don't have a valid match here. We do this a lot with our. We have to report data to state EMS agencies at my company, and a lot of times the users will pick something that doesn't match a value that the state agency has provided us, because the value that the state agency provided us isn't comparable, doesn't match what they did clinically, or doesn't match what the patient showed clinically. And so in those situations, we do have to say, okay, if it doesn't match this, if there's no matchup for this state value, then you need to report a general, there's no match here, state code, so the states can update their systems. So we make use of something similar to a default statement a lot in our decision structures where I work. If we look at a legitimate example, here I've got one that deals in grade. Now, grade contains a string that is the letter grade they earned, and in the event that the value of grade is equal to the letter A, I'm printing out the statement great, and I'm putting in a break because I don't want it to do anything else. And if the value of grade is equal to B, then I'm printing out the statement good, and I'm breaking. And if they got anything other than an A or B, I'm just letting the system pick it up and say, that's not so good. We want you to have an A or a B. So this is really good when you've got, when I've got to do all grades A through F, when I have, say, a menu system. I imagine that our phone tree system uses something similar to a switch to evaluate its options. Here's an example. In our phone tree, you've got a number of options when you first dial in. You can press 1 to be routed to the routine that calls the sales office people. When you press 2, you'll be routed a routine that puts you in our support system, which then asks you a couple more questions so that it can route you to the right person as quickly as possible. Then if you press 3, you get another option. It puts you into the routine that handles calling the training staff. If you push 4, it puts you into the routine to pick an extension. So I imagine that our PBX system, our phone routing system, has a switch statement in it. And maybe it says switch, and the test is the menu option that the user pressed. And the cases are case 1, case 2, case 3, and case 4. If they picked 1, they go to the sales office. If they picked 2, they come over to the technical support system. If they clicked 3, they go to the training department. If they clicked 4, they get prompted for an extension. And so you can see how that might avail itself of the case structure. Now, I talked a little bit earlier about making these tests, especially for the if. This really only works with the if statement, but making those tests more complex. And we can do that through the use of logical operators. Again, it allows us to make more complex Boolean statements. Logical operators allow us to combine Boolean statements using and or. And, or, and not are probably the most common logical operators used. Let's take a look at all of the different logical operators. The ones that you'll see a lot are double ampersand, and that means and. Technically, it's logical and, but it means and. And what that is that the statement on both sides of the ampersand symbol, that's the double ampersand. So that's going to be on your keyboard. That's if you hit Shift and the number 7, that'll give you what we call an ampersand. So ampersand is the logical and symbol. And for the entire combined statement to be true, the tests, the Boolean or the conditional statements on each side of that ampersand must be true. Logical or, on the other hand, is a little bit different. Only one side of that statement has to be true. Now, the way that the computer works this is if the first condition, with the and, if the first condition is tested and false, it's not even going to test the second condition. With the or, if the first condition is tested, if the first test is executed and is true, then it doesn't even bother with the second test. Sometimes we want to force those, though. So we have what's called a boolean and, which is a single ampersand. It's the same as the logical and, but forces a test on both sides of the ampersand. A boolean or is the same as the logical or, but again, forces tests on both sides of the ampersand. Then we have something called not. And not negates or makes something the opposite of what it would be. So if I had a function that returned true or false, for example, in the language that I work in, I have a function that says, it's called isDB null. And it returns true if the database field contains a null value, and returns false if the database field returns data. So I really want to know when that function returns false, or I say the question if it's not null. So if it's not null, if the function returns null, I want to know when it's not. Tells me yes when it's null, I want to know when it's not null. So I might put that opposite symbol in it. Sometimes I want to know when sometimes just because of the way I think of things, I want to flip the answer around to understand my point of view. I want it to read true whenever there's data, and I want it to read false whenever it's not. And in order to make that happen, I'm going to use the logical not. The Boolean logical exclusive OR. The way OR works is one side or both sides can be true. The logical exclusive OR says only one side can ever be true. If both sides are true, this statement is false. Either one or the other, but not both, is the best way I can find to describe the logical exclusive OR. To be honest with you, in my 10-year career, I have probably used logical exclusive OR a grand total of never. I find myself content with logical and logical OR. Those are the ones I use the most. So here's an example of a statement with logical operators. What this basically says is that both x has to be both less than y, and at the same time x has to be less than z. Both sides of this statement have to be true before this statement down here will be executed. Notice that we don't have an else here. That just means that we don't want to do anything if that statement is false. If that statement's false, it doesn't matter. We're just going to keep right on going. However, if it's true, we want something done. Now, with the OR, only one side of this statement has to be true. We don't need both sides to be true. So, your weekly hours could be less than 40, or your employee type could be P, but they both don't have to be. You could be an employee type of S with less than 40 hours. You could have 50 hours, but your employee type BP. Either way, this statement right here would execute. However, the only way this statement's not going to execute is if you have more than 40 hours and your employee type is something other than P. So again, only one side of this has to be true for the statement to be executed, not both. Up here, both. So, like I said, you could be 40 hours and P, and it would evaluate to true. You could be P and 50 hours, and it would evaluate to true. You could be under 40 and S, and it would evaluate to true. So that's the big thing. Or only one side has to be true. With and, both sides have to be true. With this comes the thought of order. I've just thrown at you two new sets of operations. So how do they fit into the grand scheme of order of operations? Well, I'm going to show you. The way the rules of order of operations go is we start with parentheses, and we execute what's inside the parentheses from left to right. We start with the innermost parentheses. Then, if we see a plus plus or a minus minus, which we really haven't talked about a whole lot yet, but we will, or a casting statement, we go ahead and execute those from left to right. We then do multiplication, division, and modulus from left to right, or then addition and subtraction, then any relational operators, and those are only going to be used in conditional statements, then equality operators, then we do our ands and ors, and then finally our shorthand notation, if we have any, our assignments and our shorthand assignment operators. Any questions on that? I've thrown a lot at you. We've talked about thinking about Boolean statements. We've talked about flowcharting our decision making, so we can more easily translate that over to something the computer can understand. We've talked about how the computer understands that stuff. We've talked about relational operators and how they give us the Boolean statements necessary to make our decisions. We have talked about making decisions in Alice, the use of the if structure in Alice, how the various types of functions and how what they give back to us affects how we have to set up that if statement, and all of that stuff still applies to Java. When we talked about Java, we talked about the two types of if statements we have there, both the if and the switch. We've talked about how those are set up and work, and then finally we wrapped everything up with logical operators. It's a lot to chew on. It's an awful lot to chew on, but it's important stuff, and it's stuff that makes our programs very useful. To have our program analyze data and make a decision is probably one of the most powerful things we can have our programs do. I'm still amazed at the thinking that goes on behind the scenes, and all of it is done by looking at data and making decisions, and it all boils down to these basic decision structures. I think the next best thing for you to do at this point is to, first of all, email me if you have questions, or you can bring them into class, and then we can come back. Then what I want you to do is, once you've thought about your questions, I want you to go ahead and try the practice exercises on the upcoming slides and look at those walkthroughs, because I think they'll help answer some of those questions you still have. Of course, if you have questions at any point or run into trouble, please feel free to email me, bsimbeck@ccac.edu. Again, thank you for watching this presentation. You can go ahead and move on now and start working on the exercises. Thank you.